Good afternoon, everyone. Today we are going to continue from where we stopped. In our last class, we analyzed for the shorter span, then we provided the reinforcements. Today we are going to continue analyzing the log span of the same panel 1. All right. We are going. That's the log span of that panel. Eh? Log span. Now in one of the classes, our moment coefficient for the log span was taken to be moment coefficient was taken to be for the positive moment was 0.034, while for the negative moment was 0.045. Right? This positive movement is used to calculate the moment at the midspan, while the negative moment coefficient is used to calculate the moment at the continuous edge. Now, our UDL was equals to 14.52 kilonewton per meter square. All right. Now, our new D will now be equals to 124 minus 12 equals to 112 millimeters. All right. Now, when you are now providing for this reinforcement, we are now minusing the size of bar away from the 124. When you are now providing for this reinforcement, you will now say Y12 so near bottom, because we are going to design for the midspan. Now, it goes straight to the span. The span equals to 4.1125 meters. All right. So we now move straight, calculating for midspan moment. All right. Okay. Now the midspan moment M is equal to, talking about midspan now, we are using the positive coefficient 0.034 multiplied by UDL 40.52 multiplied by the span 4.1125 square. This one will give me, if you go to your calculator, you compute, this one will give me 8.36 kilonewton meter, which is equivalent to 8.36 exponential 6 Newton millimeters. All right. Now, we now move straight to calculating for K. The level unknown. K is equals to moment. That's 8.36 multiplied by 10 raised to the power 6 over concrete cover was 20 multiplied by B, which is 1000 multiplied by D, our D, 112 square. This must be less than or equal to 0.156. All right. Now, when you compute that, 8.36 exponential 6 divided by 20 multiplied by 1000 multiplied by 112 squared. This one will give me 0.033. You see, this one is less than 0.156. All right, we use the lesser value. Assuming we calculated for K and it gave us a value bigger than this, we now use this value. All right. Now we are now going to LA now, the lever arm. All right. LA is calculated 0.5 plus square root of 0.25 minus K, our K, 0.033 over 0.9. All these are constants. All right. Now, if you solve for this one now must be less than or or equal to 0.95. Alright? So when you solve for this and you discover that it's greater than 0.95, you use 0.95, use 0.95. So you're now going to have 0.25 minus 0.033 divided 0.9. Let's give us this one. Alright? Square of this one will be square answer 0.46. So if you compute this, you're going to have 0.5 plus 0.46. This is equals to 0.96. So 0.96 is higher than this one. Alright? You adopt this value. You use this value. So we now calculate for Z. Z is equals to LA multiplied by D. LA multiplied by D. This is equals to our LA now is 0.95 multiplied by our D 112. This will give me 0.95 times 112. Now I'll give me 106.4 millimeters. Alright? So we will now move ahead to solving for the AS. Alright? AS is the area of steel required. This is the area of steel required after analyzing this structure. Alright? The steel required is moment, which is 8.36 exponential 6 over 0.95, a constant, multiplied by characteristic strength of steel, which we took to be 410, then multiplied by our Z 106.4. Alright, this one will give me 8.36 exponential 6 divided by 0.95 times 410 times 106.4. Okay, this one will give us 201.7 millimeter square. Okay, this is our area of steel required, for the structure to be safe. Now you will now go back to the steel table to now provide, and if you go to that steel table, the least value of area we have there is 377. Under normal circumstances, I was supposed to provide that 377. But again, we are also talking about the strength, then the size, the standard size of steel we have. So because of the sizes of steel we have, I cannot provide 300 mm. I cannot use will not provide Y 12 mm diameter at 250 center to center near bottom. Alright, the short span, from the short span, mid span, we said that one was bottom. Right, that's the first one you run. Then this one now is the second one that you now run, which should now form the distribution. Okay, now we are now going to look for the AS. AS provided now. AS provided will now be equal to please let me get the DS. It's not here with me now. Let me quickly get it. Yeah, the area of steel for 12 mm 250 center to center will be 452. 452 millimeters. So when you are not checking for deflection, you make use of this area. This one divided by this. Use that to check for deflection. Okay? So we have been able to calculate, analyze the mid-span moment of the long span. Then we provided Y12 at 250 center to center near bottom. The area is this. Subsequently, we will now do the deflection, analyze, calculate for the deflection to know if the structure is safe. Then we move to the continuous edge. Thereafter, we move to panel 2. So all these one will be analyzing all this while they are panel 1, to make sure that panel 1 is safe. Okay, so that is that for that today. Thank you and God bless.